Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So thanks for inviting me here. So today I'm going to talk about probabilistic models for parsing images. So what do I mean by parsing images? So roughly speaking, parsing images is like to understand an image like we see it. For example, if we see this tiger image, what actually do we see? We see a lot of things. We could see that there's something in the middle of the image. It may be brown in color. It may have a very distinctive texture pattern of black stripes. And maybe we see this image as have tiger in the middle and then water and grass in the background and sand in the foreground. And maybe we also see it's an outdoor wildlife scene. And we not only just know there's a tiger, we also know exactly where the tiger is. And we possibly also know all the parts of the tiger, say the head, the eye, the back, and the tail. So it always amazes me that how many things we actually see quite effortlessly by just taking a simple glance at the image. Now, of course, it will be very difficult to make a computer see all these different things. I probably don't have to repeat all those arguments why vision is hard. But there's one extra complexity here is that there are so many things at different levels of abstraction, like we have a color and texture here, we have object and scene recognition, and we also have the segmentation problem. And somehow they all have to be put into a single framework. So how would we approach this problem, say, as almost like a grand challenge of vision? So here's a classical view of visual processing. And roughly it's organized into 3 levels. At first you have the pixels and features that can be computed from pixels like color. And then at the mid-level you have you group the pixels into contours and regions. And then finally you can recognize objects and scenes from these groups. And in terms of algorithms, then at the low level you mostly have image processing problems. At the mid-level you have perceptual organization, and the high level you have recognition. So this are nice in theory. Of course, this is oversimplification. In practice, from a modern point of view, there are actually a lot of interactions between these layers. The information does not just flow from low level to high level. So what eventually I want to do, and part of which I will try to demonstrate in this talk, is that I want to put these things into a unified framework so I can have something that handles all these levels of abstraction, including the representations, the pixels, contour regions, and objects, and the visual cues associated with them. And most of my work is focused on this mid-level of perceptual organization. Now, this is not only because that the mid-level vision received much less attention than, say, image processing or object recognition. It is also because that I feel because the mid-level vision actually joins together pixels to the objects, and in my own opinion, it's actually a very important link in the whole system. Of course, that's a debatable point, and many people actually ignore this mid-level vision. And a classic example would be, say, Markov random fields on the pixel grid. Okay, so that's Markov random fields is probably the first example of probabilistic models, generic probabilistic model for images. And it is of course very natural. You have the pixel grid, then you have labels for each pixel. You link the labels to the pixels, and then you can add interactions between neighboring labels. And then you have the Markov random field. I think it first came out in that seminal paper of Gaiman and Gaiman in 1984 on stochastic relaxation and Gibbs distribution and image restoration. And since that paper, the Markov random fields has been very popular. It's been applied to many fields like image restoration, edge detection, texture synthesis, segmentation, etc., etc. So it has been successful. It has been popular. But there are problems, and the major difficulty I see is that there's not much there's not much knowledge you can put into this kind of random field. It has actually very limited representational power because you can only add interactions between, say, adjacent labels, or maybe in a small neighborhood. But that's just not that much that you can do. A few years ago, we actually did some empirical work on a pixel-based Markov random field for contours. And so we came up with empirical evidence that it's actually not good enough for natural images. But instead of going into the technical details of that analysis, I'd rather go back to images and try to develop more intuition. So let's look at this tiger image again and to say, let's look at the eye. Even I'm nearsighted, I have no difficulty seeing the eye. And I can tell which direction the tiger is looking at. And well, I could say that maybe there's even a touch of sadness in it. But if we zoom in, then it all disappears. All that we see is just a bunch of pixels. And we can't really see anything inside this blob. And the reason is actually these artificial boundaries that we introduce between the pixels when we zoom in. It somehow disrupt our perception of a longer range structure. And that happens all the time. If you work with images, you see it all the time. For example, we could zoom in the mouse and we see the same thing. So intuitively, to me, like building a probabilistic model on the pixel grid, it's almost like trying to figure out things from these zooming images, and it's very difficult. And the reason is that we have no way to represent structure on the pixel grid. And if you can't represent it, then you can't reason about it very well. OK, so here's the outline for my talk. I've already talked about the problem of parsing images, the possibility of having a framework to combine all the levels of abstraction and the importance of structure. The next will tell you a solution that we came up with is trying to build a mid-level representation based on edges. And then on top of the representation, we'll talk about probabilistic models for mid-level vision, including contour completion and figure ground organization. And I'm going to show you quantitative results on these problems. And then next, I will show you how to extend the model to include both mid-level and high-level vision and apply to problems of object segmentation and hopefully more interesting about finding people. OK, so how can we build a representation that has more structure in it? Let's start with edges. So we take an image and we just apply an edge detector. Theoretically, we could use any edge detector. The particular one we use is the one we developed at Berkeley a few years ago. It's called PB, Probabilistic Boundary. The nice thing about it is that it combines like brightness, texture, and color contrasts. So all you get, could say, is just boundaries between homogeneous regions. And you can threshold the edge map and get something like this. And so the underlying working assumption would be that so these kind of edges actually represent structure that you can detect from the image signal. Now, so what can we do about this edge map? What we do is that we try to decompose it and build a piecewise linear approximation of the edge map. So suppose these white contours are what you actually detect from the low level. And we could recursively split these contours until each piece is approximately straight. So from these white contours, we can get these vertices and these red lines. So this partial graph is approximation of the original edge map. And it's a compact representation. So here's how it happens for a real image. For the elephant, it will decompose the contours into these pieces. It's roughly speaking, it's scale invariant because if you have a straight line in the image, it will be like one straight line in the graph. So it's actually fairly efficient because it only, like, say, put vertices where the curves are, where the boundaries are curved. So if it's a straight line, you don't really put anything in the middle, so it will just become one straight line. So that's a nice representation, but there are problems. And one particular difficulty is that, of course, the edge maps are never perfect, so there are gaps in the edge map. So what can we do about that? The particular technique we use is we use constraint-denial triangulation to complete those gaps. So constraint-denial triangulation is just a variant of the standard-denial triangulation. It's actually quite popular in computational geometry. And so here is our partial graph. We have these vertices, and we have these red lines from the edge map that we want to keep. And then the constraint-denial triangulation will just fill in the rest and to also partition the image into a triangulation. And here's what happens with the elephant image. So the black pixel here, I can hardly see the laser point, but the black pixels here are from the edge map, and the green pixels here are the completions by the CDT. And we have empirical evidence that the constraint-denial triangulation is very good at completing gaps. But let me just show you an example. Here's a zooming image of the elephant. And there are a couple of places where the contrast is very low. So you can hardly get any boundary there. And here's the triangulation. You can see that the constraint triangulation correctly fill in these gaps by putting some green boundaries there.
There will be cases where it
Yeah.
makes errors.
Yes, it's not perfect. Like it's a bottom-up process, so it's never perfect. But so in order for it, say, to make an error, you have to have two vertices, both are very close to the gap, and that actually is very rare, because
Well,
now
if you have foliage, for example, right?
That's
If you
true.
have pure foliage, you're in trouble.
Yeah, that's
Which
true.
A lot of cases where you're wrong.
So
How do you know which of those green lines would have to be changed completely?
so I will talk about that later. Right now, it's just candidates. So right now, I'm not worried very much about having these crazy completions. All I care about is that I have the candidate there. Yeah.
So, is there, or maybe you'll get this later, but is there a reason, because Delaunay basically, what you're going to do is say these two edge points are the closest, so we're going to put a line there.
Mhm.
Why not say 10 closest points to me, create lines for all of them? Obviously, that'll create a lot more lines, but then you always have one edge.
So we actually have some empirical analysis for that. So this is actually better than k-nearest neighbor connection in terms of efficiency. So
You
so.
never miss the-
So typically it's good enough for us because we're not trying to get the finest details out of the image, but like we do have some analysis that this is better k-nearest neighbor. If you're interested, I can show the results later. But yeah.
We have lots of time for this talk, so I
Okay.
hope you don't mind if we interrupt.
Should I
When you
slow
say-
down a
no,
little bit, or-
You're fine, but
Okay.
when you say we have empirical analysis, I'm just curious in general, what was the methodology? Did you
Okay.
capture-
Yeah. Let me just show you the slide. Oops. Sorry. Okay. So I have edge pixels from the edge detector and have the completions. And then I will match them to the ground truth boundaries I have. So I have this data set of natural images segmented by human subjects. And I'm going to measure like how many, say, the recall ratio here is that what the percentage of the human boundaries you can recover from my edge map. So we always measure things this way. And this one is actually just showing that there's very little loss of structure when you go from pixels to triangulation. So that's kind of the methodology we use. We always use human marked boundary as the ground truth and measure against.
So that's that. I remember that database was published about 3 or 4 years ago.
So yeah, so it first came out in ICCV 2001.
Okay.
And then the Charles and David Martin extended that database a little bit, so make it bigger. But essentially the idea is in 2001.
Right, and they were hand labeled with a variety of people for each label, right? So
Yes.
you can see which labels which this is.
Yes.
Okay, thanks.
Thanks. added. So, yeah, let me just show you the data set since we're at it. So there's this large collection of natural images, and each of them is segmented by a couple of human subjects undergrads at Berkeley. And so these are the results. And I'm going to take these boundaries, these segmentation boundaries, as my ground truth. So I'm trying to make my algorithm so that it will produce the same boundaries as in these segmentations. So these are not just low-level edges. These are actually object boundaries. So there's actually a lot more we need to do before we get there.
But I guess for us, different people have different interpretations, right? So how do you know which is the right one to use?
So,
like for example, I would segment the pyramid seems different.
So you can actually have some quantitative measure and compare the segmentation from different people. And you mostly see that they're mostly the same. Some of them segment more details. Some of them are lazy. But they are more or less consistent. You can actually measure that.
Right. What I'm saying is that you could bias your scores based on one person's interpretation versus another. Trying to figure out what.
So each of them, if I remember correctly, each of them may be segmented by 10 human subjects. So it's quite a lot. And then we always match to all of them. So like we average them in our final score. So there's no bias toward any particular human subject. Okay. Okay, so let me go back to my talk. We've seen that the triangulation is good at completing gaps. And here's a summary. So what the representation we developed is that we take an image, we compute an edge map, we build a piecewise linear approximation, and then we compute a triangulation out of it. And it has very nice properties. For example, it greatly reduces complexity from, say, millions of pixels to maybe 1,000 edges in the triangulation. It's very fast to compute. Doing triangulation in 2D it takes almost no time. It's roughly scale invariant. It's like if you have straight lines, then it becomes one edge in the triangulation. So it tries to keep the large scale structure. And so we actually have, again, we have empirical evidence that it completes gaps, and so there's little loss of structure. Okay, so from this point on, I'm going to build up my models on top of the triangulation. So to use a term that we coined up a little bit earlier, we can imagine this process as building superpixels from pixels. So what do we mean by superpixels? Superpixels are, say, perceptually meaningful units that are, say, homogeneous in color or brightness or texture. So we're going to use superpixels exactly the same as pixels, like as atomic units. And this is actually closely related to a principle of uniform connectedness that Palmer and Rock proposed in 1994 as a principle in perceptual organization. And it's not perfect because it's built up on image signal, but I'm going to show you that it's actually useful in many cases. And it's not only a reduction in complexity. For example, it also allows us to model longer ranges of interaction. So go back to the Markov model. A pair of pixels is just a pair of pixels, but a pair of superpixels could like span 100 or 200 pixels. So that's a larger structure that you can represent.
So, sorry.
Yes.
I'm kind of curious. Why do you do it this way as opposed to, like each year color segmentation, you get regions, therefore each region becomes superpixel, for example?
Yes. So the idea of superpixels actually it doesn't require any particular segmentation algorithm. You can do anything. So the reason I did this is that I really like scale invariance. I really like to keep those long straight lines in my representation. And if you do any color-based segmentation, they don't give you that. And also, like this is more like edge-based. I think edges are important, so I'm happy to have an edge-based approach. And efficiency is also a concern. this one you can do very fast. So at the end, I'm going to show you a video. That's why you can do that very quickly. But yeah, you could definitely do mean shift. So this process, like from the edge map to the triangulation, is actually scale invariant. But my edge map is actually not. So
why not?
so when you compute the edge map, you have to compute, say, at some scale.
Yeah, you did it at scale.
So the edge map has to compute at some scale. So anything, say, below a threshold, those fine scale structures, you don't see it. Okay, so that makes the process not exactly scale invariant. So in order to avoid any like arguments, I put that first. But I'm certainly happy that.
You do sort of multi-scale anything.
You could do that, but as of now, like we don't really have a very satisfactory answer to multi-scale edge detection. Like we have a scale space, but that's more like signal-oriented. And for edge map, where there's a large scale structure, like we don't have a very good answer for that. So for the moment, I'm going to use edge map for a single scale.
Not points themselves when you break the curve, so scale invariant.
That's scale invariant. That's scale invariant. Yeah. Okay, so let me make an analogy with natural language processing. So the parsing images is almost the same like parsing languages. You have these different levels of structure, and you try to make an inference combining all of them. And one distinction here is that like we don't really have the equivalence of words in your images. The pixels, they contain very little information in themselves. So they are more like letters than words. So you can think about what we did is to introduce an intermediate level that just like words. So superpixels like words. They have meaning by themselves, but also they have to interact with each other to get a high level of structure. Okay, just an analogy. So I've talked about the mid-level representation, and then let's see what we can do with it. So mid-level vision, I want to say a few words. Mid-level vision, it's not low-level vision that you can compute it from a neighborhood. And it's not high-level vision, and we don't have like notions of objects or scenes in it. And here are the important problems in mid-level vision: curvilinear grouping, figure one organization, or region segmentation. And I'm going to talk about these in turn. So first, I will discuss curvilinear grouping. So let me do this very quickly. So what is curvilinear grouping? It's based on a very simple, but I think it's a very fundamental fact that boundaries in nature are smooth. Okay, and based on the fact there are quite a few visual phenomena associated with it, like good continuation, visual completion, or illusory contours. And I don't want to go to the details of any of these, but it suffices to say that it's a well-studied problem in psychophysics, and people generally think that curvilinear grouping is very important as part of the perception. So let's say, from a practical point of view, what we care is that we could actually use that to get a better edge detector. Now, we actually have some evidence from human vision that there's a limit that you can do with local edge detection, and we are more or less there at the limit. So let me show you an example. So here are a few patches, and I want to ask a question that whether there is an edge in the middle of the patch. And just from this small patch, it's really hard to see what's actually happening. But if you bring in more context, then it suddenly becomes very obvious that you have boundaries here, but not here. Okay, so this obviously, like, there's limited amount of information in a small patch, and if you can bring in more context, then you can do better. And smooth boundary is a very important contextual cue. So let's see how we can set up this problem. It's actually very straightforward. We have this underlying graph, the triangulation we have, and we can put a random variable on each edge. And a binary random variable, say 1 if it's a boundary and 0 if it's not. Okay, And then we can try to make inference about these random variables. And what we do is that we put a random field on top of the graph. And we will add in features so that we define a joint probability distribution on all the variables xe. And my goal is to estimate the marginal distribution of each xe. Okay. And the particular technique we use is conditional random fields. It's actually quite straightforward. And so we have this collection of random variables. I'm going to introduce two type potential functions. I'm going to have some potential functions on the edges, and I'm going to have some potential functions on junctions. Okay, I'm going to combine these two types of junctions, basically multiply them together, and this is my probability model. This defines a joint distribution of x. Okay, z is just the normalizing factor. If you've seen it, then it's trivial, but I hope it's simple enough. So conditional random fields actually first proposed in the natural language processing community for parsing languages. And if you put that into a terminology of graphical models, then it's not so surprising. It's just undirected graphical model with potential functions in the exponential family. Okay, you can see here, so these are, the fees and size are my features, and this is just a log linear combination of the features. That's actually the simplest possible that you could do. So now let's look at the model and to see what potential functions I use. So what are my edge potentials? It's actually easy. So imagine, so remember that for every edge in the triangulation, it corresponds to a piece of boundary in the original image. Okay, so I can always carry the information over and measure the average contrast on this edge. And that's going to be my edge feature. So that's the signal from the low level. Okay, and then I'm going to consider the interactions of these the edges at the junctions. And you can actually model the degree of the junction this way. Imagine a junction here with these random variables. The degree of the junction actually depends on the values of these xe's. Okay, so if they're all 0, then this is a degree 0 junction, means there's no line here. And if it's 1, 0, 0, then it's degree 1 junction, it's a line ending. And similarly, you have, say, a continuation of contour and a T-junction. Okay, so you can easily write out this formula and to put that into a potential form of potential function. So basically, what we do here is that we give a different weight for each type of the junction. So I'm going to have different weights for line ending, continuation, or T-junction. Okay.
You also do x? Is that a degree 4?
We have that, yes, but it's actually not that important.
But the degree of a junction, if you ignore the labeling, the degree of a vertex, right?
Mm-hmm.
The order of whatever vertex can be large, right? You can have 5 edges or something.
Mm-hmm. Yes, yes.
So you've got the original, the maximum degree, right, which is the number of things coming in.
Mm-hmm.
And then you have the actual degree, which is if you only count the 1 labels, right?
So this one, so you can put maximum. Say I only consider degrees below 4, for example.
I see. Okay.
And then you ignore all the higher order
Okay,
junctions.
so empirically, you found the up to 3 matters, and the higher ones don't really matter.
Yeah, they never occur in natural images, so they should not be so important for this inference problem.
Yeah. I mean, they rarely occur. I think a cast shadow on top of an albedo edge is an extra.
Yeah, we have
right?
degree 4, but we don't have anything above 4.
I see. Okay.
Okay. So we can also put continuity into it. So this is for a degree 2 junction only. When you have 2 edges turned on, then you can actually measure the angle between them, and then you just put that into the potential function with something about the angle. Okay. So this is all very straightforward, but then you could actually like very nicely model the degree of junction and the continuity in this probabilistic framework. And the one nice thing about conditional random fields is actually you can actually efficiently learn the parameters. And so here are the parameters that we learned. And these are weights for penalty or integer terms. So the lower it is, the more likely it's going to occur. So we see that this is the most likely case where there's no line. And also the continuation is better than, say, a line ending or a T-junction. Now, you could actually compare that to what Gaiman and Gaiman had in their original 1984 paper. They have like almost the same thing. They have the like no line, line ending, turn, or continuation, and T-junction. So the difference is that they set these parameters by hand. They don't really have a good way to learn these parameters. And also because their model is on the pixel grid, so they can only distinguish case between the turn, which is 90 degree, and the continuation, which is 0 degree. But now we could actually use that angle explicitly. So I hope you agree that we have made progress here. And it's a combination of a couple of factors. We have mid-level representation, we have a probabilistic framework, and we have large annotated data sets, natural images. Okay, so now let's move on and let me show you the results. And I'm going to show you the results in the form of precision versus recall. So let me explain. So suppose this is my edge map. Okay, I want to know how good it is. And suppose the red curve here is the segmentation boundary given by humans. So I want to see how good they match to each other. So I just do a bipartite matching between the black pixels and the white pixels. Okay, after I do the matching, then I can count precision as the pairs matched pixels divided by the total detections. This is how accurate you are in your detections. And also recall is the percentage of the red pixels that you recover. And so they will come out as a precision recall curve. So the reason why it's a curve is that the edge map is usually soft. So you can vary the threshold to get the curve. So for example, here is if you set the edge detection threshold high, then there are relatively few detections, low recall but high precision. And here you have high recall but low precision. And that point is actually the ideal point.
The question, when the create a database, get users to actually draw the boundary.
Yes.
So is there a snapping tool that allows them to snap the regions or something, or they just sketch?
So the tool we used actually, there was no snapping, but you could zoom in and out and refine the boundary, so it's fairly accurate. Yeah.
Another is, at some point you're discretizing it to these little line segments.
Mm-hmm.
Is that would be very sensitive. So one curve might choose to break it up into these segments, and then another might be 3 segments.
Yes.
And another very slightly different curve would be only 2 segments.
Yes.
How do you compare like those 3 segments?
So this evaluation, it's always on the pixel grid. So I get the marginal distributions on the edges, then I map them back to the pixel grid, and then do the matching.
But is there some sort of distance threshold in there, also some distance measure? Because again, like two straight lines,
Mm-hmm.
pixels are going to be slightly different pixels than 3.
So remember, I have the triangulation picture. You have the black pixels and the green pixels.
Right.
So I actually keep the black pixels from the edge detector. So although in the abstraction it's a one straight line, and it's actually a bunch of pixels. It's a curve in the underlying image.
Right. But then when you add the completion.
So the completions are straight lines. Yes.
And it seems like there's a funny measure.
Um,
Some sort of distance.
So there is a distance threshold in this matching, but so this evaluation process is actually independent of the triangulation. So this is a generic evaluation that's applicable to any edge detector. Yeah.
So, when the users were asked to segment the images, it seems like you're kind of comparing apples to oranges here a little bit, because they were asked to segment the images into objects, right? Into what the users saw as objects. Is that correct?
So the instruction is that you just segment the image. So it's not really like you have to segment out the objects. It's very vague.
When the user's doing this, they're going to be using a higher level of information.
Yes.
That's there.
Yes.
It seems like a better task would be if you had these like kind of images that weren't of actual objects. I mean, I don't know how you create these images, but they would be like something that we wouldn't be able to use our higher level knowledge in segment, and then we could segment them and see if this does the same thing. Because it seems like whenever a user comes in and tries to segment like this elephant, you're immediately just gonna go around the edge of the elephant and say it's there. Segment. And this is using high level information. And it's kind of it seems like it's not really comparing the same thing because you're never using this high level information. And if you weren't, it seems like you ideally want that green curve to go up to 100%.
Yes.
You'd always want to err on having too many edges because I assume that at some point you're going to bringing in this high level knowledge, and then at that point, then you're weeding out a lot of edges. So before you actually bring this high level knowledge, you're going to want to have a lot of extra edges in there potentially to do this segmentation. Does that make sense?
Yeah, certainly. So the way we set up this benchmarking strategy is that we try to not to distinguish, say, between mid-level algorithms and high-level algorithms. So we just have one single measure is how good you match to these object boundaries. So it's kind of like we set the bar really high, and if you don't use high-level knowledge, then you can't get there. But at least we could see how much progress we're making by approaching that limit. And this is like eventually we want only those object boundaries.
But do you think you're maybe answering the wrong question then? Because you might be trying to maximize this position recall curve. But in reality, if you're going to make this really, really work, you might need to have a worse position recall curve where you have more edges detected, and then throw the high level on top of that. You see what I mean? Like, if you look at the whole system as a whole, you might not want the same result as just trying to maximize.
So for the results I'm going to show you, it's actually not that relevant because I'm going to show you that it's a complete dominance input signal. So if you have something that's considerably better, say in terms of precision, then it's not really that serious a question that okay, I should keep more pixels, maybe like the threshold thing is basically varying the threshold so you can get say higher recall values versus low recall values.
Because an alternative question I might ask is, if I want to get 100% of the user-specified edges, how many false edges do I need?
Okay.
Maybe let's say 9.
Okay. Yeah. So that will mean that I don't care about precision, but I want to push recall.
Yes. So
yes.
Then we never reached that.
Yes, we've never reached 100%. But if you compare the red curve, which is the input, and the green curve, which is the output, and the green curve is doing better than the asymptotic recall value.
For sure, we can lower the threshold on the red until it's eventually going to hit 100. You can check that.
No. Okay.
Everywhere, and that would put you in the lower right-hand corner, but that's trivial algorithm.
Yeah.
It's hard to argue that that's an interesting design point, right? I mean, I agree that because the green dominates, it's always it's an advancement because you can just throw away the red initial stuff, and you're always satisfied.
Red curve always go up.
And so it's a precision recall curve. It's like ROC curve, but not exactly ROC curve. So it could go up and down. It's possible. So I've shown you these results. This is on a hosted set of 350 images. And you can see that curvilinear grouping helps boundary detection in all the range of recall value. So that's quite comforting. And now, if you allow me to exaggerate a little bit, I want to say that this is a piece of evidence that mid-level vision is actually useful. Well, because edge detection is a very fundamental problem in vision, and now we can do better on that. So I haven't shown you any, say, particular application, but I hope this is like a piece of evidence. Okay, so let me show you some examples. So the way I visualize it is that I set the threshold such that you have the same number of black pixels in both of these results. Okay, so you choose the threshold so that they have the same number of detections. And you can see here that the conditional random field model helps to find continuous boundaries and also suppress noise in the background clutter. Okay, and here are more examples on another data set of baseball players, and we see the same phenomenon here, that you get smooth boundaries out of this model.
That's kind of strange. If you go back to your previous slide, mean, there are like some of these on the left, I guess the PB ones actually seems more informative to me. Because it has more details in there, and I can tell more about the one on the image than the one on the CRM.
So this is one is on a particular threshold. So like it's not like we're missing the boundaries here. They are just of a lower value. So if you lower the threshold, you actually see those boundaries. Well, it's debatable whether this is more informative or that is more informative. And all I can say is that the quantitative measure shows that this one is doing better at detecting the object boundary. So this one is doing better at detecting the boundary of the horse. No, I'm just generally talking about the idea. So we're already seeing that in terms of the curve. This is just an example. Yeah, we can debate this point with which one is more informative, and especially for human perception. And well, the small boundaries are nice, but maybe you actually want some, like, we can do completion ourselves from just a few pixels. So that may be the reason that this turns out to be more informative. But the task is different. Okay. So, okay, how much time do I have? I think I'm running out of time, so I will try to be quick. So I've talked about the curvilinear grouping, and we can talk about another problem of figure-1 organization. And so I'm sure you have seen these ambiguous figures. We either see the faces or the goblet. And so to set up this problem, it's a piece of boundary, and you either perceive the boundary belongs to the left side, and then you see the face, but not the goblet. And if you perceive the boundary to the right-hand side, then you see the goblet, but not the face. So there are many examples of this. It's important for the perception of shape. But there has been like no work on figure-1 organization for natural images. And so we came up and collected a data set for that and tried to do something. And it's actually exactly the same. Imagine I have this graph and have all these random variables. So originally I have one boundary versus non-boundary, but now I have, say, left versus right. Okay, so I'm trying to label these boundaries as left side is figure or right side is figure. And it's the same. I can put a random field. I can put some local cues, and then I'll put a conditional random field to enforce the consistency at the junctions. And so without going into details, let me just show you the results. So the chance is 50%. The local model, the best we could do is like 64.8. And assuming you have a perfect segmentation, you just take the average of local cues is 72. And then the conditional random field finally get you up to 78. And the self-consistency of the data is 88%. So this is actually quite promising. This is the first results on natural images, and it shows that it's actually possible to do figure-1 assignment or figure-1 organization without too much effort.
What does data set consistency mean?
So people actually label the boundaries differently. Some say this is left, some say that is right.
So one human against the sort of average, that's how well
yeah.
on average.
Yeah. So I've talked about these two problems of curvilinear grouping and figure-1 assignment, and they're quite the same. You have online structure, you get these random labels, and you have a conditional random field to enforce the consistent junctions. So to put a little more history, this is like line labeling that dates back to the 1960s. So in that problem, you have this kind of objects, you have these possible junctions, and you solve a constraint satisfaction problem to get those labels. So we're almost doing the same thing. But we're doing it with modern technology, and we're shooting for more realistic applications. Okay. Yeah, so I've talked about these models for contour labeling. Then there's more we can do. Say we could add region-based cues. We could do joint contour and region inference. And more importantly, we could get object knowledge. And so here's what we do. We took an input image. We want to produce a segmentation of the object. So nominally, it's very hard to do because the appearance of the object may not be, say, uniform. But you have a lot of training data of the same object, and then it becomes much easier because you have a lot of object-specific cues like shape or origin support or characteristic texture. And so the setup is also straightforward. You have these random variables on edges, and then you could put these random variables on the triangles. Okay, and then you could have an object node which encodes, say, location, or scale, or pose of the object that you're looking for. And then all you want to do is to have some probabilistic framework to link together all these variables. And so how can we link together all these variables? Then we have these queues of low-level, mid-level, and high-level queues. And so without going too much of these details of these, basically the object level queue, like shape, is very important. And the way to combine these is that in the random field, you just do a log linear combination of the queues. It's quite straightforward, although this looks complicated. And here are the results. Sorry, I rushed a little bit.
It's okay. We don't have to finish in an hour. We have an hour
I see.
Allocated. So
Okay.
if you want to just back up a few slides, why don't you take us through some of these cues a little bit? Just spend a minute explaining
Okay.
what they are.
So just remember, these x variables are the edge variables. These y's are the origin variables, and the z is the object node. So at low level, you can measure, say, the edge contrast, or maybe the brightness and texture similarity. Okay, these are the low-level cues. And at the mid-level, we're already seeing the junction type and continuity. And
So,
then
sorry, the edge I understand because it's in contrast. So x will be on when it's when you have a strong edge. Y, S, and T are what, binary variables?
So YT are triangle variables.
Right.
And so this is just saying that if you have the same label, then they should be similar in brightness and
What's
texture.
the dictionary of labels?
1 if it's foreground, 0 if it's
Oh, I
background.
see. Okay, so you're
So I'm
saying
doing
that-
object segmentation.
So neighboring triangles are more likely to have the same label, but not.
Yeah.
Okay. Go ahead.
Yeah. So at the yeah. So at the
color texture, that's why they're dependent on I.
so at the mid level, then I've talked about the junction and continuity, and you have the consistency between x and y's. So if x is 1, then y's should be different, and vice versa. And then for the high level cues, and then you have like shape or the support of the horse, and then you have familiar texture. Say.
So the texture similarity, I understand.
Mhm.
It should be foreground if it's in that dictionary. And then the Z is what?
Z is the say the location of the horse, the center of the horse.
Oh, okay.
So if yeah, let me just talk a little bit, see if I can get this through. So if I know, say, the center of the horse is say somewhere, and then I know relative to the center of the horse where the legs should be and where the back of the horse should be, and they all have a distinct shape. Like the back, it should be horizontal line. The legs, you should have a pair of vertical lines, and etc. So you can capture that relationship and put a constraint between, say, x and z.
That's a constraint on the contour lines.
Yes.
Given a specific location of the horse.
Yes.
And we're assuming the horse is kind of in the center.
Yeah. Yeah. And similarly, you can put a constraint between y's and z. That's basically, if you know the center of the horse, then all the triangles close to the center should be part of the horse. Okay. So it's actually not that complicated. And let me just show you the results. So we have seen the red curve and the green curve. The red curve is low level, and the green curve is low plus middle. And then the blue curve is low plus high, meaning you have low level signal, and then you have the object knowledge. And then the purple one is where you combine all these three together. Okay, so you see that the object knowledge is very useful. You have a very big jump from the green curve to the blue curve. But also you see that mid-level vision is still useful here. There's a difference between the blue curve and the purple curve. Not much, but it's still there.
Do you have an example where, I'm not sure about to show this, but of the blue and the purple one? An image showing the blue result. and showing the purple result.
So here's the purple one. So
Okay.
I don't have the results for the blue one, but here's the way you combine all the cues together. So you have the image, and then you have the input edge map. And then you get the output edge map and the segmentation mask, and then also the center of the horse.
And
So-
again, these exemplars were all more or less at the same scale, right?
So they are more the same scale, and they are more or less the same pose. It's our horse roughly standing facing left. So you do get a lot of mileage from knowing the shape of the pose of the object.
In the output contour, you've got sort of a transparency value.
So remember, this is the marginal posterior. So it's not binary. So you see some of the contours are weak, some of them are strong.
By the triangle.
I'm sorry.
The Y, the triangle.
Yeah, these are the marginals on the triangles. So you also see some transparency effect and some triangulation artifact.
And
but-
X is that Z variable, it's the XY
Yeah,
center.
yeah. So these are all marginals, marginal posteriors.
How does this compare to, like, John Witness did the high-level segmentation and then
Um,
more data set, I think. Where you use segmentation and high-level finder to get a segmentation.
So we mostly compare results, say, to the Bernstein and Woolman's work, and they have some follow-up on the same line, and so we actually do better than theirs. And also, I mentioned there's this object cut paper in CVPR last year. They actually do better than us, but their model is fairly more complicated. So they use color, and they actually use the parts of the horse. So this one is fairly generic. This is not assuming we know that what parts the horse consists of. But I think this results are competitive in terms of the results on these grayscale images. And I want to point out the last one. This horse is very funny because it has this black patches and white patches. And so if you want to do a segmentation from the low-level point of view, then it's hopeless because it's not uniform color. But if you know it's a horse, then you can actually do pretty well. Okay. So now I've talked about the horses, and now talk about something hopefully more interesting. It's about finding people. So what I want to do is that I want to take an image of people and then figure out where the person is and where the joint locations are. And this is, of course, a very challenging problem, and mostly because there's too much pose variation in terms of the articulation and self-occlusion for the human body. But then also you have the problem of closing, lighting, and background clutter, and etc. And so normally what do? People do top-down approaches. So what they have is that they have the pixel level, and then they have the object level, which is the human body model. And they just combine them together. And there are two possibilities. You could do a 3D model-based detection or tracking. But unfortunately, it's a large degree of freedom and fails most of the time. Now, you could do 2D template-based matching, and it requires a lot of training data. And so what we want to do is that instead of, say, this top-down approach, rely heavily on the object model, we do something, say, we go to the superpixels first, and then we combine with the object model. And we could also possibly do something, say, without actually considering the object. We combine the superpixels with the mid-level model. So these are two possibilities. And because I always do this pre-processing of superpixels, we call that bottom-up approach. So how can we find people from bottom up? So people, it's just we see that as a collection of body parts. You have the torso and the limbs. And so first we could say detect candidate parts from the image. So this is the bottom up part. You detect candidates, and then you try to assemble them together. And so we're going to use the superpixels to detect body parts, and we're going to use integrated programming to assemble the parts. And now, I'm not sure if you want to know the details of that, but let me just show you the results. So here are some results. You have the original image from a skating sequence. You have the edge map, and then you have the detection which labels the torso and the limbs and also the segmentation mask. So this is a single frame detection. I'm not using skin color in particular, and I'm not making any assumption on pose or on scale. So this is, I think this is actually quite good, although right now the approach actually doesn't work on every pose, but still for a large variation of pose, it could find people just by using the configuration constraints between body parts. And here are more results on some different images. And so though they're not perfect, but I think, yes?
The mapping you're trying to find is you're trying to figure out what the pose is for each of the parts, right? You have a linked model for the
yes.
geometry.
Yes.
And then an assignment of which superpixels map to each part?
Okay, so let me actually show you the details. So the way we detect body parts is that we look at the triangulation, and then we look for parallel lines. Because like triangulation is a scale-invariant process, so if it's a straight line, then it's just one edge in the graph. So that makes our job much easier. Just look at parallel lines. And the bottom there, I show you the candidates. The first one, I think, is the top 10 candidates for the body parts, or maybe top 20. But anyway, so here are the top candidates. And you see that we get some good detections on the body, and we miss some of them, and we get a lot of false positives in the background, because we're not actually using skin color or anything. But then you could actually, so there I show you all the candidates. So the advantage of the bottom processing is that it greatly reduces the number of candidates. If you do top-down approach, then you have to look at every possible rectangle in the image. But if you do bottom-up, then that's the only set of possibilities you need to look at. Okay, and then here's actually the assembly problem. So you have all the candidate body parts, these line pairs in the image, and then you have the model for the human body, and you have all of these labels. So basically, you want to assign these labels to the candidates. And so we have. So the nice thing about the integer credited programming framework is that you could consider constraints on all pairs of assignments. So normally when you do dynamic programming, you can only look at, say, the adjacent body parts. But now you can actually look at all possibilities. Okay. So, so this, I don't consider this, say, as a final product or a final system, but I think this shows that it's actually fairly promising to do single frame people detection if you have a good mid-level model, I would say, more sophisticated image processing. So let's look at another problem related. It's finding people in video. So the problem changes a little bit if you have the whole sequence to look at instead just of a single image. You have a lot of additional information, say motion, or maybe you have a good idea of the appearance of the human body, and maybe you also have temporal consistency. Now the question I want to ask is that how much can we do without using the object model? So in single frame detection, you have to use the body model, otherwise there's no clue. But now, can you do something without the body model? So here's the diagram I use. So without actually using object knowledge, what can you do? So this is like tracking people as blobs. Now, people normally think that it's actually difficult if there's a lot of variation in the pose, because the human body is not a rectangle. But I want to say that blob tracking is actually not rectangle tracking. So here's our the outline of our system. So we have the frames coming in, and at each frame I do a figure ground segmentation. Okay, so I use signals from the single frame, but I also use signals. But I also use cues. For example, the appearance of the body, and also use temporal coherence that I get from the previous frames. So I have all this information, then I can do a figure one segmentation to segment out the human body. So that's the we do. And here's an example: the original image and the one on the top right corner is that how much you can do with just the appearance model. So you build up an appearance model from the first frame, and then you test it. So you can see that it's actually quite good, because in this sequence, the appearance doesn't change that much, but it also gets a lot of background clutter. Okay, so you can not do that very well. And then on the lower left corner, you have the edge map they can compute from single frame. Again, it's quite good. You can get sharp boundaries at the legs, for example, but also there are places where it's confused, for example, on the torso. So neither of these two sources of information is reliable enough. But if you combine these two and adding the mid-level cues, such as the continuity that I talked about, and with a little bit temporal coherence information, then actually you can actually segment out the human body. Okay, here's another example. Again, like neither the appearance model alone or the boundary map alone can give you the segmentation, but if you put them together, it's possible. So now let me show the results. So these are the preliminary results. So it's not perfect yet, but I hope that's enough to demonstrate that if you can do repeated segmentation, then you can do tracking. So I'm showing, yeah. Okay. So again, the original image, the appearance model, the boundary map, and the final segmentation. So the segmentation is not perfect. It works in most of the frames, but sometimes, say, you have the arms missing, or maybe there's some confusion with the background. But most of the time, it's actually working quite good.
Is this run as a batch process or online? In other words, does the frame only get to look at previous information in time or all information in time?
Previous. So this is online system. So I'm not doing any, say, clustering or anything.
There's no particular model that this is a person with.
Yeah. So this
foreground, background.
This is just a foreground background segmentation. All I know, there's an object in the middle of the image.
And the system doesn't have a danger of latching onto the wrong appearance model, that it sort of decides something's part of the skater and then propagates that?
So right now, I'm only using appearance from the first frame.
I see.
So then there's no drifting problem. But the hope is that if you could do segmentation, then drifting is less an issue if you compare to the case where you use rectangle.
And the first frame didn't have any human intervention. It
Uh,
got what it got.
So that's the first frame. I actually draw a rectangle around it.
I see.
So
Yeah,
where it starts. So maybe let me play that again. So one can argue it's not that difficult to sequence, but there's actually quite a bit of challenges, like background clutter, and say the arms are only a few pixels wide, so you get a lot of motion blur, and also sometimes you get quite big apparent motion. So I think this is quite promising. You can do a lot of things on top of this. You can put a human body model, then you figure out where the limbs are. Or maybe you can do active recognition directly from these results.
I mean, you can also do background just differencing, and it would get rid of a lot of things, right? Because you have, in this particular case, because it's a panning camera, you can build up a static background model and do differencing. Right?
Yes. So, but I'm not trying to like make any special assumption about the motion of the camera. I just want to say the camera is moving.
Right. Good.
Okay. So. I think that's the end of my talk. So just to conclude, I've talked about the intermediate level representation using superpixels. And I've talked problems on contact completion, figure grounds, object segmentation, and finding people. So there are a lot of future work I could do. I could try to build a more consistent and rich representation. I could make the random fields more complicated. I could try to use this representation for general object recognition, and I could try to do tracking and finding people. So that's all. Thank you very much for listening. And this joint work with my colleagues at Berkeley, Charles Focus and Alex Berg, and my advisor, Jitendra Malik. Okay.
Thank you.
Thank you.